Welcome to the online presentation of this 2024 WACV paper. I am Tim Schoonbeek and I'm here to present our work, IndustReal, a dataset for procedure step recognition handling execution errors in egocentric videos in an industrial-like setting. Here we see an example of a procedure logbook. Such a logbook denotes what happened at which moment during a procedure, for instance, a maintenance or an assembly action. We see an expected time, which is the expected duration for each procedure step, as well as an actual time. We also see the delta between these two. A logbook such as this can be created by pressing a start and stop button whenever you are starting an action, or by measuring how long a user looks at a certain instruction. In this case, we see that the first step took 2 hours longer than expected, and that all the subsequent steps, which is 2 hours of work, was performed in 1 minute. In this case, the user only kept looking at the first instruction whilst performing all of the subsequent steps. This got us thinking, can we automatically recognize procedure actions, even when maybe things go wrong? Because if we can automatically log where the operator is and prevent them from having to click on the start and the stop button. And simultaneously, we get a more accurate logbook from the service action. What about current industrial action recognition approaches? Well, they lack on a couple of aspects. Firstly, they do not provide any measure of completeness or corrections for the recognized actions. Secondly, the procedure knowledge often has to be learned and is not explicitly provided. This requires a lot of data. Finally, 3D geometry, for instance CAD data, is rarely used, whilst this is frequently available within the industrial domain. We fill this identified gap in literature by proposing the new procedure step recognition task, which generates real industrial value by recognizing correctly completed procedure steps. Alongside this, we present the new IndustReal dataset. First, let's focus on defining the procedure step recognition task. The goal of procedure step recognition is to extract an estimate of all procedure steps correctly performed by a person up to time t. We can simply write it down as a function of f, which is some computational model, which takes as input sensory inputs, for instance, video or audio, and a descriptive set of the procedural actions. The latter is key because using explicit information about the procedure, we can reduce the number of training examples that we need to feed into our network. In order to quantify the performance of a procedure step recognition system, we define 3 metrics. The first is the procedure order similarity, which focuses on determining the quality of the predicted order. This is based on the Damarau-Levenstein edit distance. Then we propose to use the F1 score and the average delay in seconds. We have just defined the new task of procedure step recognition, which focuses on recognizing correctly completed procedure steps. In this work, we also present IndustReal, a new dataset specifically created to stimulate research on this new task. IndustReal contains 6 hours of RGB, stereo, depth, gaze, and prose tracking data, various execution and procedural errors, and has accompanying CAD data for all the parts. Additionally, it is benchmarked for procedure step recognition, action recognition, and assembly state detection. IndustReal differs from other datasets in the literature in various aspects, but most notably in procedure complexity and in the provision of 3D models. More details on this can also be found in the paper. Also, the IndustReal is entirely 3D printed, which means it is easy to reproduce, to adjust, and to contribute to. The industrial dataset contains two procedures. Firstly, we have the assembly procedure, as outlined in the top of this slide. Then we have the maintenance procedures, or a part upgrade, which is shown in the bottom. This figure shows an overview of a sample from the industrial dataset. We can see the different modalities. So on top, we can see the RGB plus the gaze and the hand joint detection. We can see the stereo left and right images, and we can see the depth and visible light sensors. Below that, we can see the annotations, and we can see that we have annotations for action recognition, assembly state detection, and procedure step recognition. So far, we have defined our new task, procedure step recognition, which focuses on recognizing correctly completed procedure steps, and we've presented a new dataset, IndustReal. So now let's combine the two by performing procedure step recognition on the new IndustReal dataset. As input, we take RGB video sequences and procedural information. From the video sequences, we train an object detector to perform state detection. This state detection is fed into our baseline 1, so B1. B1 is naive. If it sees a new assembly state, it will determine the steps required to reach this state according to the procedure information and adds these steps to the predictions. Baseline 2 also takes the assembly states as input, but after determining which steps are required to reach this state, it accumulates these based on the confidence of the prediction. And once a confidence for a step, so not a state, but a procedure step, exceeds a threshold, this step is added to the predictions. Finally, we have the third baseline, which is the same as the second baseline, but with an added filter that only steps that are expected within this assembly or within this part replacement can be added to Y-hat. Let's see an example of procedure step recognition on IndustReal. In this case, it's the third baseline, model B3. We can see that as the user shows a clear view of the object state detection algorithm recognizes a completed state, and that this is translated into predictions for completed steps. This table shows the performance of procedure step recognition on IndustReal. Note that the S denotes exclusively training on synthetic data. Let's focus on B3 for now. We can see that synthetic data alone drops the performance of the model significantly. We can also see that we get an increased performance with more explicit procedure knowledge. And this effect is extra large for using only synthetic data. So we can use this explicit procedure knowledge to compensate for the worse detections that we see for synthetic data. Here we see a common fail case for the baseline, a false positive prediction on execution error. Can you spot the mistake? Good job if you did. We can see that the user used the wrong nut on the front of the vehicle. As mentioned, we have also provided annotations for action recognition as well as assembly state detection, and further details of this can be found in our paper. To conclude, we have presented the new computer vision task, procedure step recognition, which can create real industrial value by recognizing correctly completed procedure steps. Alongside, we have presented a new dataset, IndustReal. If I've caught your interest, if you have questions, or if you would like to collaborate, please don't hesitate to contact me or to come up to my poster. Thank you for your attention.